So this next segment is really kind of getting into the experimental half of kinetics. Now, you may remember earlier in the chapter, I did mention that it is really impossible to do anything other than find the rate law of a reaction through experimentation. Now, I know that's kind of contrary to what I just showed you. I did show you that you could write a rate law directly from a one-step mechanism, and that is still true. But part of the problem is that when you step into the lab, the chemical reaction doesn't have like a big sign around its neck announcing to the world that it's a one-step mechanism. So unfortunately, we as scientists need to assign or just kind of assume that nothing is. So what would this experiment even look like in the lab? Like, what do you actually do to try and find a rate law? So let's look at kind of a phony little reaction here. A plus B makes C plus D. Now, if this is a one-step mechanism, I would assume that rate would be equal to K times the concentration of A times the concentration of B. But it might not be. What we really want to do is to design an experiment which will elucidate what is the order with respect to A and what is the order with respect to B. So really, the only thing that we can do is to do something that will change the rate of that chemical reaction. As long as we hold all the conditions the same, the rate constant should not change, and that's a very powerful thing, because now I'm moving on to the one thing that I can actually manipulate, and that's concentration. So what we end up doing is we do a chemical reaction where we may monkey with the concentration of A and see what happens to the rate. Mathematically, I should be able to figure out what this exponent is, depending on what I did to my concentration and what it does to the rate. Then we'll do a second set where we'll actually change the concentration of B and then see how that affects the rate. Now, while we're doing that, we'll want to hold the concentration of A constant. Now, once again, I really think it's a good idea that I show you an example of what one of these problems is going to look like. Now, experimentally, it's actually kind of fun. In the lab, you would quite literally just be adding different amounts of A and B together and sitting there with a timer and seeing how long the reaction actually took to try and monitor the rate as a function of time. Now, the data that would come out of a reaction or a series of reactions that would look like this would be something like this, where we do 1, 2, 3 different trials, and we do these 3 different trials with a different concentration of A and a different concentration of B. And we look at how that actually affects the overall rate of the reaction. So again, what we need to do is to try and figure out how does changing this concentration actually affect my rate. So when you're looking at this data, again, you can't work with 2 variables at the same time. You need to see if you can compare something where one of these concentrations is actually held constant. So my personal suggestion here would be, let's compare the first reaction and the third reaction, because what I see is that my concentration with respect to A is not changing. What that allows me to do is to only look at what's happening to the concentration with respect to B. Now, going from the first reaction to the second reaction, what I see here is that I've doubled the concentration. Can you see that you've doubled the concentration? So if I'm examining this, what I'm really looking at here is what is the effect of rate when I change the concentration of B? And I'm really trying to figure out what is this exponent right up here. Well, between experiment 1 and experiment 2, again, I can compare them because I have not changed my concentration of A. That means that there's no effect with the concentration here. It's only changing rate because I'm changing the concentration of B. So I've doubled that. So what I'm going to do in this little just mock-up is to put in a 2 for how I've doubled my concentration. And now let's look at how that's affected the rate. Well, oh my goodness, it hasn't affected the rate at all. So the rate here is exactly the same. Well, then what should the order be? If I change this concentration and absolutely nothing happens to that rate, my exponent can only be one thing, and that is 0. In other words, changing the concentration of B absolutely does not affect anything with this chemical reaction. So far I know that the order with respect to B is 0. Well, let's rinse, repeat, and let's see if we can figure out now what's happening with the concentration of A. I'm going to go ahead and I'm going to compare experiments 1 and 2, where I'm doubling the concentration of A. Now, I'm sure that you can see that you're also tripling the concentration of B, but it doesn't matter because we already know that its order is 0 and it doesn't affect the reaction. So what I'm looking at now when I'm comparing experiments 1 and 2 is I'm looking at how the rate changes as I change my concentration of A. And I'm going to be looking to see what exponent would best fit this data. So because I double my concentration, I'm just going to kind of pseudo plug a 2 in there. And let's look at what happens to my rate. It looks like here my rate doubles. So I'm going to put a 2 in for my rate as well, because my rate doubles when my concentration doubles. So mathematically, we're looking for what is the only exponent that holds this mathematical statement true, and that has to be a 1. So rate equals the concentration of A to the first. Now we do need to plug all of this into one seamless equation. What we were really examining was what is the order with respect to A, and what was the order with respect to B. Well, we figured out that A's order is 1. We figured out that B's order is 0. So let's write it in now. Rate equals K times A. Now I'm not going to write a first, and I'm not even going to bother to write B into it because it had no effect on the overall experiment. And I think maybe another example might help figure this out just a little bit more. So let's get into a second example. I just happen to have them prepared for you here. Again, we're looking at the reaction of A plus B. And I don't know the orders with respect to that reaction yet. So at the end, what I'm hoping to figure out is if I have rate equals K times A, what is the exponent with respect to A? And what is the exponent with respect to B? So again, what I'm going to do is kind of examine my data. And what I notice here between equations 1 and 2 is that my concentration with respect to B is being held constant. And what that's going to enable me to do is to figure out what A's influence on the overall rate is. And I'm sure that you can see between experiment 1 and experiment 2, I am actually quadrupling my concentration with respect to A. So I'm examining this in this little substep. What is the effect of A on the rate? So that we can just figure out what this one order is. So again, I'm going to put in a 4 for A because I'm quadrupling the concentration. If I take a look at what happens to the rate, I also quadruple the rate. You can actually punch this into the calculator. If you enter in 4.0 times 10 to the negative third and multiply it times 4, you will get 1.6 times 10 to the negative second. So my rate is also going up by a factor of 4. Well, the only exponent that would actually make this make sense is a 1. So the order with respect to A is first order. Now I'm going to go back and I'm going to examine my data because I still need to try and figure out what B's influence in fact is. And unfortunately, I noticed that I don't really ever hold A constant. But that's okay, because you know what? I already know what A's influence is. I know that its order with respect to A, it's going to be first order. So I think I'm going to go ahead and I'm going to look at experiments 1 to experiment 2. So for this one, I know that rate equals K times A to the first and B to the I don't know what. Now we're not going to include K as part of this because quite honestly, it's a constant and it's okay. We're just kind of showing proportionally what's happening to the overall rate. Now, what I have done to my overall concentration is it looks like I have multiplied my concentration of A times a factor of 2. So I'm going to go ahead and put that in for my A, 2 to the first. Okay, well, let's look at what we did to B. 0.05, how do I get to 0.2? Well, it looks like I need to quadruple my concentration to get it to a 0.2. So I'm multiplying my concentration of B to the fourth. Okay, I still don't know what this exponent is. And what happens to my overall rate of the reaction? Well, that goes up by a factor of 8. If you actually throw into the calculator 4.0 times 10 to the negative third, and you multiply that times 8, you will get 3.2 times 10 to the negative second. So my rate's going up by a factor of 8. So now I just have a little bit of math left over to do, and luckily it's pretty simple. So I know 8 is going to equal 2 times 4 to the y. Let's divide this 2 over. So 4 equals 4 to the y. Well, this exponent only makes sense as being one thing, a 1. So the order with respect to B must also be first. Now we can write our overall rate law. So rate must equal K times the concentration of A, and we previously established that that's going to be to the first, times the concentration of B. That's also going to be to the first. Now, these problems do take some time to get used to, but generally speaking, as long as you're trying to find this mathematical relationship between when I change this concentration, what happens to my rate, and thinking about it in terms of this is an exponential relationship. So if I double my concentration and I quadruple my rate, then that's second order. But if I double my concentration and I double the rate, then that means that that's going to be first order. I think that you're going to be okay. Now, like I said, these problems do take some practice. So I do have a practice set of problems ready for you. And just let me know if you do need any assistance. I'm very happy to help you.